Warm greetings, everyone. Neutrino physics is largely an art of learning a great deal by observing nothing. With these striking words of Haim Harari, I, Dr. Poonam Jain, member of Executive Council, Indian Association of Physics Teachers, Regional Council 1, wholeheartedly welcome you all for the second vibrant lecture series organized by Indian Association of Physics Teachers, Regional Council 1. The title for today's lecture is The Mass of Small Things. I would first like to pay my sincere gratitude towards Professor Ajoy Ghataksar, the President, the National Academy of Sciences of India, former Professor of Physics, IIT Delhi, for gracing us with his presence on this auspicious event. Also, I would like to welcome our renowned speaker of the day, Professor Amitabh Ray Chaudhary, sir, Professor Emeritus, Department of Physics, University of Calcutta, former Palit Professor of Physics, University of Calcutta, and former Director, Harish Chandra Research Institute, Prayagraj, Allahabad. Now, I welcome to our all the other distinguished professor and the members of Indian Association of Physics Teachers, Regional Council 1, and our virtual audience present here. Before we begin, this is to inform you that this session is being recorded and streaming live on YouTube and Facebook. Before proceeding ahead, I request all the participants to mute their mics during the session for the smooth conduct of the event and drop your questions related to lecture in the chat box. Now, without further ado, I request Dr. M.S. Bhandari, the Secretary, Indian Association of Physics Teachers, Regional Council 1, to welcome our distinguished guest and give introduction about IAPT RC1 and its activities. Over to you, sir.
Thank you, Poonamji. On behalf of IAPT, it's my privilege to welcome our guest of honor for today's lecture, Professor Ajoy Kumar Ghatak, President of National Academy of Sciences of India, former Professor of Physics, IIT Delhi. I welcome our distinguished speaker, Professor Amitabh Ray Chaudhary, former Palit Professor of Physics, University of Calcutta, and former Director, Harish Chandra Research Institute, Prayagraj. I welcome all the faculty members from Delhi University, NCERT, schools, colleges, universities, IITs, IISER, NISER, members of IAPT, and DSTF. First of all, I would like to introduce IAPT to all our honorable participants who have joined us first time. IAPT is a major and well-reputed organization established by Dr. D.P. Khandelwal in the year 1984. IAPT RC1 has local chapters in every state of India. IAPT RC1 is the local chapter for Delhi and Haryana. At the central level and RC level, we organize various activities for the promotion of physics and physics education. Here are some of the activities.
Excuse me, sir.
Yes.
Sir, your video is off. Kindly switch it on.
No. Okay. Sorry.
Yes, sir. It is fine now.
Vedratna Memorial Lecture. In this program, eminent scientists from physics fraternity enlighten us with their extraordinary work and give us valuable knowledge about the subject. IAPT holds regional competitions on innovative experiments in physics. It holds training workshops on hands-on approach of teaching physics. In this program, our main focus is on making learning of physics more interesting and comprehensive. At the central level, IAPT organizes various examinations of international repute. Some of them are National Standard Examination in Junior Science, popularly known as NSEJP, This examination leads to International Olympiad in Junior Science, National Standard Examination in Physics, Chemistry, Biology, and Astronomy, popularly known as NSEP, NSEC, NSEB, and NSEA, National Graduate Physics Examination, NGPE, and many more activities are to mention. Today's lecture is the fourth in the series. All the lectures are available on IAPT RC1 channel on YouTube. With this, I again welcome our honorable speaker, Professor Amitabh Ray Chaudhary, distinguished guests, and respected participant. Thank you very much. Poonamji.
Yes, sir. Thank you, sir. Thank you for introducing IAPT to all the new participants and the participants present over here. Now, I would like to request Professor Ajoy Ghataksar, the President, National Academy of Sciences of India, former Professor of Physics, IIT Delhi, to introduce our distinguished speaker of the day. Over to you, sir.
Yes, can you hear me?
Yes, sir.
Okay. Thank you very much, Poonam. Welcome to this lecture. I have a few slides. First of all, I would like to congratulate Professor Srivastav, Dr. Bhandari, Dr. Poonam Jain, and all the others at IAPT for organizing lectures by such eminent scholars. Such lectures will enthuse the younger generation to take up science as their career and contribute to the nation. So these slides that I have made yesterday, so these are particularly meant for the younger generation. And I am very glad to see there are 170 participants here today. So I thank Professor Srivastav for asking me to introduce Professor Amitabh Ray Chaudhary, and he is seen here teaching his students at University of Calcutta. He did his BSc from Presidency College in Calcutta. This was the first college of higher learning in India. Presidency College was the first college established in 1817, 200 years back, by Raja Ram Mohan Rai, who along with 6 others donated their personal wealth to establish this college. The pioneering discoveries made by Jagadish Chandra Bose and Prafulla Chandra Ray were made in the laboratories of Presidency College. The younger generation must know the great works of people like Jagadish Chandra Bose, Acharya Prafulla Chandra Ray, and which has contributed to the development of science in India. And he did his MSc from Delhi University in 1973, and I'm sure he was taught by Professor D.S. Kothari, who was also my guru. So Professor D.S. Kothari was an authority in the general area of quantum mechanics. He carried out his doctoral work at University of Maryland in College Park, USA, under the supervision of the outstanding professor, Oscar Greenberg, in particle physics, and received his PhD degree in 1977. He did postdoctoral work at the University of Oxford and at TIFR. In 1980, he joined Calcutta University. Professor Ray Chaudhary has made outstanding research contributions in particle physics, including grand unification, the Higgs boson, neutrino physics, etc., etc. But he also,
sir.
Yeah.
Sir, kindly make it slideshow so that we can read it out.
You cannot see any slide?
No, sir, we can see the slides, but it is not in the slideshow mode. So make it full screen once.
It
so
is
we
full
can.
Screen.
No, sir, it is not. Yes, sir. Fine. Absolutely fine. Thank you, sir.
Did you see the previous slides? Did you see this one?
No, sir. Now we can see.
Okay, I'll just repeat. So
sure.
he did his BS. He did his BS. Can you see now?
Sir, it's absolutely fine.
He did his BSc from Presidency College in Calcutta. The younger generation must know that this was the first college of higher learning in India, established in 1817 by Raja Ram Mohan Rai, along with 6 others, who donated their personal wealth to establish the college. That is very important. And then the pioneering work of Jagdish Chandra Bose and Prafulla Chandra Ray were made in the laboratories of Presidency College. And he did his MSc from Delhi University, under, I'm sure, Professor D.S. Kothari, who was also my teacher, must have taught him quantum mechanics. And then he carried out his doctoral work at University of Maryland under the supervision of Professor Oscar Greenberg, who is an authority in particle physics, and received his PhD degree in 1977. He did postdoctoral work at the University of Oxford and at Tata Institute of Fundamental Research in Bombay. In 1980, he joined Calcutta University. Professor Ray Chaudhary has made outstanding research contributions in particle physics, including grand unification, the Higgs boson, neutrino physics, etc., etc. But he holds a tremendous reputation of a charismatic teacher among his students. He's also the nephew of Professor Amal Kumar Ray Chaudhary. As most of you would know, he made outstanding contribution. There is a famous Ray Chaudhary equation in general theory of relativity, for which he is extremely well known. Because of his outstanding research contributions, Professor Amitabh Ray Chaudhary received the most prestigious Shanti Swarup Bhatnagar Award and is fellow of all the three National Science Academies of India. He was awarded DSc honoris causa by the University of Gaurbanga and the University of North Bengal. And University of Maryland honored him by making him the International Alumnus of the Year 2005. This is, in my opinion, a great recognition of his outstanding work. He was also the director of the very famous Harish Chandra Research Institute in Allahabad, which is a premier institution dedicated to research in mathematics and theoretical physics from 2005 to 2011, after which he rejoined Calcutta University, where he became the most coveted Palit Professor of Physics. And I thought, I will tell you who are all before him. C.V. Raman, I'm sure all of you know him. D.M. Bose was a great cosmic ray physicist and also a nuclear physicist. And then Meghnad Saha, who was the president, who founded the National Academy of Sciences, India. And Professor B.D. Nag Chaudhary, who made the cyclotron, along with Professor Meghnad Saha. Then Chanchal Majumdar, who is an authority in the general area of solid-state physics. He was also a very close friend of mine. And now we have Amitabh Ray Chaudhary. I must tell you, Taraknath Palit was a lawyer and a philanthropist. He was associated with the Swadeshi movement and was one of the key figures behind the establishment of Calcutta University and Jadavpur University. This was pre-independent India. He died in 1913 or 14, and he donated 15 lakhs to Calcutta University to create the Palit Professor of Physics. And Professor Ray Chaudhary was honored with this Palit Professorship of Physics. In the United States, great educational institutions have excelled because of philanthropy. So you see, Taraknath Palit was a philanthropist. And in India, we require more such philanthropists. And the dictionary meaning of the word philanthropy is the practice of giving money and time to help make life better for other people. It's a very profound concept. And I think all the younger generation must be aware of it. You see, even the founder of Presidency College, he gave his own money to create that college, from which came out outstanding personalities, Amartya Sen, Amitabh Ray Chaudhary, and many others. So we have to develop this practice of giving money and time to help make life better for other people. And in 1929, Louis Bamberger and his sister, Mrs. Felix Poole, donated 1929, just after the American Depression, $5 million for the creation of the Institute for Advanced Study at Princeton in the state of New Jersey. We must have such people more in India. It was there in the pre-independent India, but not so much in the post-independent area. So with these few words, I have tremendous pleasure in welcoming Professor Ray Chaudhary and give his talk on the mass of small things. We are very grateful to him for agreeing to speak to us and enthuse the younger generation to take up science as their career. Thank you, Amitabh.
Thank you so much, sir, for such a nice introduction. I am feeling personally privileged to have the words from such an eminent professor here. I hope our participants will also relish each and every word of this lecture. Thank you so much, sir. I again welcome Professor Amitabh Ray Chaudhary, sir.
Thank you. Shall I begin my talk now, or shall I wait?
Yes, please. Start your share your
Okay.
screen and
Very good. So I'll share my screen. Thank you. Yeah. Whoops. Just a minute. Give me a minute. I think I did something wrong, which I shouldn't have done. So in a moment, I'll be back. Yeah. Is this screen shared now? Hello?
No, sir.
Not yet?
No, sir.
Okay, just a minute.
yes.
It is here. Now let's start from the beginning. Is it there now? Is it okay?
Yes, sir. Yes, sir.
Yes.
Perfectly
Very
fine.
That's very nice.
Very good. Yeah, I first want to thank Professor Ghataksar. Professor Ghataksar, I've known him for a very, very long time, of course, and he has been very kind with his words. I don't deserve any of those words, and I feel very humbled by what he said. There's one thing which I want to touch upon, which is he mentioned Professor D.S. Kothari. And I feel that I owe a great deal to Professor Kothari because he used to come and have a special lecture. He was then, when we were in Delhi University, he was already chairman of the UGC. So he was very busy elsewhere, but he used to come every Saturday to give a 1-hour lecture. And he would open some page of the book by Dirac on quantum mechanics. And he was so thrilled. The expression from him, it was obvious that it was very thrilling to him. But it was all Greek and Latin to us. We didn't understand a word of what Dirac was saying. After a few days, we realized that we must learn this book. Otherwise, we will not be able to share Professor Kothari's joy. And I think that entirely changed our career. Now, before I go on, I first have to thank Professor Srivastava, who contacted me to ask me to give a lecture in this program. And I must thank Professor Srivastava for this offer, and I agreed immediately. And I also thank the other organizers, the Dr. Poonam Jain, who has been in contact with me, Professor Bhandari, and all the other members. And of course, the rest of the audience. I know that there are many people who know already the stuff which I'm going to talk about. But I'm hoping that there are a few relative newcomers to the field, and they will find something interesting in what I have to talk about. What I plan to discuss today is about mass of small things. Now, of course, if something is big and we know how to calculate its mass, we have to take the product of its density with the volume, and that will give the mass. But for an elementary particle, for example, we cannot calculate mass that way. So we have to define this origin. So we discuss about mainly the origin of the masses of such particles. Before that, I define what is mass and then the equivalence principle a little bit. And then most of the talk is on the mass of the elementary particles and the Higgs mechanism. I briefly mentioned the standard model. I don't go into any details. But the important thing here is that the standard model requires that the neutrino is massless. However, it turns out that recent experiments indicate that the neutrino is massive. So there is some physics which is beyond the standard model, which we still do not know what it is. And that's an open question, which the junior members in the audience will answer in their lifetime. Then there are other open questions like the Majorana fermion and the Majorana mass of the fermion and dark matter and so on. If I am unable to complete the Majorana fermion and the dark matter, please excuse me. It's more important to convey a feeling about the subject than to try to cover a lot of things in great detail. I'll come back to this part a little later. So what is mass? Now there are two ways in which we think about mass. One is the gravitational force, where mass enters in this formula, and the other is Newton's law, where mass enters in this formula, force equals mass times acceleration. Usually this mass, the one which enters in Newton's law, is called the inertial mass. It tells how a body responds to a force acting on it. So the acceleration is determined by this proportionality factor. Whereas the other mass is called the gravitational mass, which determines the force of gravitation. So this is the formula for the force of gravitation. And here this quantity mass enters. Now there is the equivalence principle, which says that the gravitational mass is the same as the inertial mass. Now this is a very, very strong result. It's a strong result because, as I say, I use this symbol to imply, to mean that this result implies motion of a particle under a gravitational force does not depend on its mass. How does it come about? Because you see, the force depends on is proportional to the mass, and the acceleration is forced by the mass. So therefore, if we look at the acceleration of a particle in a gravitational field, then it will not depend on its mass. So therefore, all particles, irrespective of their masses, move in the same manner in a gravitational field. So therefore, their movement in the gravitational field has got nothing to do with the particle itself. So then it must, the only other thing on which it can depend then is space-time itself. So therefore, the motion of a particle in a gravitational field must be dependent only on the space-time and nothing else. And this is what motivates general relativity, which formulates space-time as a geometrical object. Another way in which the equivalence principle is sometimes focused upon is that one cannot distinguish between two situations. In one situation, a body is accelerated in a lift, for example, with going upwards with the acceleration due to gravity, with a force such that the acceleration is the same as small g. And the other situation is where it is at rest, the lift is at rest, but the acceleration due to gravity is acting. So in these two situations, in one situation is the gravitational mass, which is relevant. In the other situation is the inertial mass, which is relevant when there's a force acting on the body. And these two situations are equivalent according to the principle of equivalence. Now, all this is fine, but we have to ask ourselves, what is the origin of mass? How does an elementary particle have a mass. Now, the only way an elementary particle can have a mass then is through interactions, because if it has no structure, then its mass must come through interactions. And this is a view which is also espoused by Feynman, that mass is due to interactions. It's a measure of inertia, as we know, mass is a measure of inertia. And if a particle has many interactions, like if you can imagine two situations, a particle moving, let's say, in vacuum, and a particle moving in water, let us say, then the water will have interactions with the particle, and therefore the particle will find it more difficult to move, and therefore the interactions effectively give rise to a mass of the particle. So mass is a measure of inertia, and more interactions make it difficult for the particle to move. Now, before I go on to discuss the masses of various kinds of particles, I have to make a distinction between bosons and fermions. As we know, there are two kinds of particles, and they are distinguished by their intrinsic angular momentum, which is called spin. It's an attribute of an elementary particle, which arises from quantum mechanics, and is measured in units of h over 2 pi, where h is Planck's constant. Now, according to quantum mechanics, the spin of a particle is either half integral or integral. So it can be, if it's integral, then it can be 0, 1, or 2, and so on. And such particles are called bosons, and they respect the Bose-Einstein statistics. So here is a picture of boson, of Professor Bose, and this is a picture of Bose condensation. The other kinds of particles which have half integral spin, that is, for example, spin half or spin 3/2, remember, all in units of h over 2 pi. Those particles of fractional spin are called fermions, and they obey the Fermi-Dirac statistics. This is Enrico Fermi, the Italian physicist, who came up with the idea of Fermi statistics. Now, these rules are very important for us because they control the behavior of, for example, atomic structure, of the Higgs field, and so on. And they will keep cropping up in the lecture as we go along. And now, what are the elementary particles? There are two kinds of elementary particles broadly. On one side, I have the fermions. These are the fermions in this block. And in this rightmost column are the bosons. Now, the bosons are the carriers of force. Einstein has told us that there is no action at a distance. The force between two particles, if there is a force between two particles, then that must be mediated by some intermediary which is exchanged between the two particles. And those mediators are always bosons. And here I have outlined the photon, the gluon, which is the mediator of the strong interactions, and the Z and the W, which are responsible for the weak interactions. I have left out the graviton, and I've also left out gravitation in this entire talk. Also, I should mention, these are the quarks in the first two rows. There are 6 quarks, and there are 6 leptons. The leptons do not have the strong interactions. They only have weak and electromagnetic interactions if they are charged. The neutrinos have no charge, so they only have weak interactions. They couple only to the Z and the W. I'll come back to this a little later, that neutrinos couple only to the Z and the W. quarks couple to all of the couplings. They couple to the weak interactions, to the strong interactions, and also to the photon because they are charged. Now, the force carriers were suggested by Einstein, and here we must remember that, for example, this is a diagram, the Feynman diagram, which shows how an electron interacts with another electron through the exchange of a photon. Now, all interactions have their own mediators, and the weak interactions have as their mediator the W and the Z boson. Now, the weak interactions are short-ranged. One cannot feel the weak interactions outside the nuclear radius, so they are very short-range force. And that means that the mass of the weak boson, the mass of the W is large. The range of the interaction is related to the mass of the mediator in an inverse proportion. So if the mass is 0, then the range of the interaction is infinity. The photon has 0 mass, and therefore the electromagnetic interaction is long-range. On the other hand, the weak interactions are short-range, and this requires that the mass of the W boson and the Z boson is very large. So we have to find out ways by which this large mass of the W boson can be obtained. So this is a diagram explaining the weak interaction. In a weak interaction, as we know, a neutron, one nucleus changes to another, but the basic underlying process is a neutron goes to a proton, an electron, and a neutrino. In fact, an anti-neutrino. If the anti-neutrino had not been there, then the energy of the electron would be fixed by the parent and the daughter nuclei's mass. But we find that the electron has a distribution of energies, which means that there must be a new particle associated, and that in the decay, and that particle is the anti-neutrino, which carries off the rest of the energy. We'll come back to this later on. But at this moment, the point which I want to stress is that the mass of the W boson is rather heavy. So we have these heavy bosons and also the fermions. Now, I'm not going to go into any detail of the way the interactions of these particles are understood in terms of symmetries, but the basic point is well known to everybody. What is the basic point? The basic point is that there are some basic particles, the fundamental particles, which are the quarks and the leptons, and there are forces acting between them. The forces act through the virtual particle to the exchange of the mediating bosons, which are virtual particles. And the interactions can all be traced to some symmetries. And these symmetries are called gauge symmetries. And it turns out that there's a very nice way to formulate all of this in terms of the gauge symmetry, the strong interaction, the electromagnetic, and the weak interaction can all be neatly formulated in terms of the gauge symmetry principle. And this makes the calculations possible. Higher order perturbation calculations can be done in quantum field theory, and they agree with experimental results. So things look bright. But it is not the complete story. Why isn't it the complete story? Because it turns out that the symmetry has a price. The price of the symmetry is that the symmetry requires that all particles, the fermions, the quarks and the leptons, as well as the bosons, the W and the Z boson, must be massless. Now the photon is massless, which is good, in fact, because we also see that the photon to be massless. That's fine. But quarks, leptons, the W and the Z, these are not massless. So there must be something going on which is missing so far in this symmetry principle. The solution to that is in terms of the Higgs mechanism. The Higgs mechanism is a way by which one can keep the good features of the symmetry and yet break it in a certain way. The Higgs field is an entity which breaks the symmetry, but breaks it in a very subtle fashion. It preserves all the good features of the symmetry, the calculability, etc., and yet it allows the particles to be made massive. The Higgs boson is a wave in the Higgs field, and the Higgs boson, the Higgs bosons have been detected at CERN in 2012, as we all know. Now, the idea for this, the Higgs mechanism, and in fact, there were others who were also participants in this development, the others like Braut and Engler, and various other people, Hagen and Kibble and Guralnik. So they all contributed to it. And the Higgs and Engler, Higgs and Engler, they won the Nobel Prize for their work, for this work. Braut had died by that time, the collaborator of Engler had died. Now, you would think that such a major discovery, such a major progress would be a paper of many, many, many pages. So here is the entire paper of Peter Higgs, for which he got the Nobel Prize. This is Mr. Peter Higgs, and he got the Nobel Prize for writing this 1.5-page paper. And this 1.5-page paper, if you look at it in detail, will turn out to be nothing but an analysis of small oscillations, which is taught in classical mechanics to MSc students. Of course, this is formulated in quantum field theory, so there are some sophistications, but the basic idea is extremely simple, and it's all there in these three equations. And for just this work, Peter Higgs got the Nobel Prize. Now, you would think that, oh, if it's so easy to get the Nobel Prize, why are people struggling so hard? What's there? What's the difficulty? Well, the difficulty is that in order to make such a breakthrough, you have to have an extremely brilliant idea. And what is that brilliant idea? The brilliant idea is here. Higgs said that the vacuum, which we always thought is an empty space, is actually not empty. It's filled with what we now call the Higgs field. Here in this analysis, he has a scalar field called phi, and the vacuum is actually not empty, but rather it is completely filled with this scalar phi. The scalar phi is nowadays called the Higgs field. This is, of course, Mr. Peter Higgs, an extremely modest fellow. You can see some of his interviews in YouTube. He's an extremely good person. Now, I cannot explain the Higgs mechanism here in detail, but I'll explain the basic structure through a set of cartoons. And how does it go? It goes like this. What is the Higgs mechanism? Imagine that we have a very crowded room, and there's a VIP who enters through one of the doors of the room, and she wants to go and go through the room out through another door somewhere here. Now, if the room had been empty, she would have just walked across without any hindrance. On the other hand, because this room is actually very crowded, it will be very difficult for her to move through. So there'll be pushes and shoves and so on, and she will have to struggle to get through the room to the other side. So if this room had been empty, she would have no problem, no inertia, no mass, so to speak. But because of the filled room, she develops a mass. This is the idea of the Higgs mechanism. The idea of the mechanism is that the vacuum of the universe is not empty. It has a background, what is called a condensate of the Higgs field, and this is responsible for particle masses because particles have to struggle to go through the vacuum. They have an inertia to go through the vacuum because of their interaction with the Higgs field. Now, the Higgs field turns out to be a neutral field. Now, because it is a neutral field, so the photon does not couple to the Higgs field. So the photon has no problem going through the room. The photon has got no problem traveling through the vacuum because the vacuum is filled with the Higgs field, but the photon does not speak to the Higgs field, and it goes through merrily and it has no mass. But the other particles do interact with the Higgs field, and therefore they get a mass, they develop a mass. Now, what is the Higgs boson then? So we understand the Higgs mechanism. What is the Higgs boson? The Higgs boson is like a wave in the Higgs field. So imagine now that this is the Higgs condensate, that everything is aligned. There are all this crowded room, every space is filled up with these people, that same crowded room. And this time there's no VIP who's entering, but there's some rumor which is told by somebody from the outside. For example, somebody comes and says that India has just won a gold medal in the Tokyo Olympics. Now, when the first person hears this, the person here, he learns that India has won a gold medal in the Tokyo Olympics. He tells the next person, and then he tells the next person. So this rumor, it passes from one person to another in the room. The rumor travels. There is no VIP now. It's only a rumor that India has won a gold medal, which goes from one person to another and travels in this crowd. It's like a wave in the Higgs field. The rumor gets transmitted from person to person. The rumor travels like a wave in the medium. A disturbance in the Higgs condensate, the condensate in the vacuum, is a Higgs boson, and this is what has been detected in the standard model. So what then is the standard model? Oh, before I come to the standard model, I have to talk about something else. Now, the Higgs boson I have spoken about, and I've told you how the other particles get a mass while passing through the crowded vacuum. But for fermions, I have to make another important point before I come to a fermion mass. And that has to do with left and right-handed fermions. So what are these? Every fermion can be decomposed into two components, a left component and a right component. Now, please remember that a fermion can have associated with it two vectors. What are the two vectors? One is its momentum P, and the other is its spin, because the fermions have a spin. The spin is half for most fermions, for quarks and leptons is half. So now there are these two vectors, the momentum and the spin. And if the momentum and the spin are aligned, then by convention it's called right-handed. And if the momentum and the spin are in opposite directions, the two vectors are in opposite directions, it's called left-handed by convention. So a fermion can in general have both of these kinds, the ones which have the spin parallel to the momentum and the other where the spin is anti-parallel to the momentum. Now the crucial thing here is that the fermion mass couples the left to the right. So under parity, left goes to right, and the fermion mass couples the left to the right. Now, there is an easy way to understand why the mass couples the left to the right. Imagine the following situation, that I have a right-handed fermion with a certain mass, which is moving in this direction. Now, because the right-handed fermion has a certain mass, its velocity can be large, but it can never be the velocity of light. It has a large velocity, let us say, but I can always imagine a reference frame which is moving with an even larger velocity in the same direction. Now, if I go to that frame of reference, to that inertial frame, which is moving in the same direction, but is moving faster than this right-handed fermion, then in that reference frame, the direction of momentum would appear to be reversed. Spin would not change. So the right-handed fermion in this other reference frame would appear to be left-handed because the momentum has reversed, but the spin hasn't. Now, this key argument could be given because I said that the particle has a mass and therefore it is moving with a speed which is not the speed of light. So I can always go to a higher speed. If the particle is massless, then it is moving with the speed of light, and I can never go to another frame which is moving faster. So for a massless particle, a right-handed particle can never be made into a left-handed particle or vice versa. But for a massive particle, I must have a right as well as a left particle. So therefore, if there's only left-handed or only right-handed component for a fermion, then its mass must be zero. So taking all this into account, what then is the standard model, which is very successful experimental? The standard model describes the strong and the electroweak interaction. This is an interaction which includes both electromagnetic and the weak interactions. Is mediated by the gluons, the W boson, the Z boson, and the photon. And it includes parity violation. The weak interactions violate parity, that is included, that is built in by making the left-handed and the right-handed fermion behave in somewhat different ways. And that brings in the parity violation. And through the Higgs mechanism, via the Higgs field, the masses of the WZ, the quarks and the leptons are generated. However, at that time, when the standard model was formulated, it was believed that the neutrino is massless. So what the people did, the proponents of the standard model, what they did was they did not include a right-handed neutrino in the standard model. Now, if there is no right-handed neutrino, as I've just argued, it has to be massless. In order to be massive, a particle must have both left and right-handed components for a fermion. So the neutrino, which has only a right-handed component in this, which has only a left-handed component in the standard model, is massless. So that has been chosen for consistency of the information of that time. So there is no, this is that figure where I explain why both right and left-handed fermions are needed for a mass. So neutrinos are massless in the standard model. The standard model is very successful. However, today we know that neutrinos have a mass. So the standard model, however successful it may be, has to have some extension. So this brings me to a discussion of neutrino mass, and the neutrino can very well be imagined as a thief because it escapes with energy and momentum in beta decay, and we feel that something is lost, but in fact nothing is lost. The energy and the momentum and the spin angular momentum, they have escaped with the neutrino. Now, how do we know that the neutrino has a mass? Recall first that the neutrino is a very light, we know now it's very light. It used to be thought to be massless, uncharged spin half particle which hardly interact. It was introduced by Pauli in 1930. Their interaction is so little, so feeble, that they pass from one end of the Earth to another without any interaction almost. So therefore, they're very difficult to detect, and that's why very little is known about them. But that also has a benefit. The benefit is that even though billions of neutrinos are going through our body every time, they are totally harmless because they don't interact, and therefore we have no feeling and we have no damage because of the passage of these neutrinos. Neutrinos are in fact profusely produced in the sun, in the atmosphere, through cosmic rays, and then at accelerators they can be artificially produced, and also in nuclear reactors. In nuclear reactors, it's actually anti-neutrinos. So these produce copious amounts of neutrinos, and we need very large numbers of neutrinos in order to detect them, because they are individually very hard to detect. Now, according to the standard model, neutrinos should be massless, as I've explained, but several recent experiments show neutrinos oscillate, and this implies that neutrinos are massless. Now, the mass of the neutrino is so small that it is difficult, it's impossible as of today to measure its mass directly. However, we can measure its mass indirectly through interference effects, which is a tool through which we can always make measurements of an extremely high precision. So what is this oscillation mechanism and how does it come about? Now, let's recall first the properties of neutrinos. There are three kinds of neutrinos associated with the electron or the muon or the tau, which are leptons which are electrically charged. So these are electrically charged leptons, and these are neutral members which are partners of these charged particles. So these are the three kinds of neutrinos, and most of their properties have been only recently discovered. Now, the neutrinos only have weak interactions. They interact through the W and Z boson mediation. What does the W boson do? The W boson is charged. So either it takes a neutrino to an electron or vice versa. That's what a W boson will do. The Z boson, on the other hand, is neutral, so it doesn't change the kind of particle. And for a Z boson mediated interaction, the initial and final neutrinos are the same. Now, this will be very crucial for my next two slides. So I repeat this once again, that the W boson mediated interaction will change the kind of particle, will take neutrinos to electrons or muons or taus, depending on which kind it is, whereas the Z bosons are indifferent to the three kinds of neutrinos. All of them interact identically with the Z boson. Now, I do not go into all the details of how neutrino masses were found, but I give one example, that of solar neutrinos. The solar neutrinos come from the sun, and what happens in the sun is that four protons fuse together to form a helium nucleus and two positrons to balance the charge, because here you have four protons and here two protons and two neutrons. So there are two positrons and then two neutrinos to balance the lepton number. And in addition, it's an exothermic reaction, 27 MeV of energy. So this is the sunlight, the heat and light that we get from the sun. And just like sunlight, solar neutrinos are also reaching us, but unlike sunlight, the solar neutrinos are reaching us day and night. Why at night? Because at night, the sunlight is blocked by the Earth. But the neutrinos are not blocked by the Earth, they travel through the Earth. So in the night, the neutrinos come from below, and in the morning, the neutrinos come from above, from the sun. Now, of course, this reaction does not take place in one go because four protons don't usually come together at one point very easily. So there are steps through which this reaction takes place. And I don't go into the detail, but the basic idea is that here is shown the neutrino energy as a function of the neutrino flux. And there are good astrophysics calculations which tell us how many neutrinos of what energy we expect from the sun. So there's a robust prediction of the number of solar neutrinos reaching the Earth as a function of energy. Now, these have been detected. These solar neutrinos have been detected. However, there is a problem. What is the problem? The problem is that, now this is a complicated slide, but I want you to focus on this second column. These are four different experiments, in fact, several different experiments. And in all these experiments, one measures the number of solar neutrinos and compares it with the prediction from the theoretical model. And look at the second column. All of them find that the ratio, the expected, the observed over the expected, is much less than 1. The error bars are given, and the error bars are so small that it's clear that this is inconsistent with unity by many standard deviations. So therefore, something grossly wrong is going on. Now, the first such experiment, home stake, was started by this gentleman, Ray Davis, and he's actually a chemist by training. And he did a very clever experiment where the neutrinos from the sun would hit chlorine atoms and change them to argon, excited argon atoms. And then Davis was clever, argon being a noble element, inert gas, it doesn't interact. So he counted the argon atoms which were being produced one by one to find the neutrino flux, how many neutrinos are interacting. And he found that the ratio was much smaller than 1. So when he came out with this result, then people first said that, oh, why is a chemist getting into physics? This is too much for them, and so they should not be taken seriously, and let's not worry about him. But Davis was serious. He kept doing this experiment from the 1960s, and he kept on showing that the number was always less than 1. And after a while, people began to take note of this result, and other experiments were started. And all of them found that indeed Davis was right, and the ratio is really less than 1. Davis, meanwhile, because of this pioneering work, got the Nobel Prize. And those physicists who laughed at them had to swallow their pride, because Davis, the chemist, was given the Nobel Prize not in chemistry, but in physics. So Davis got the Nobel Prize in physics because of this work. But the question is, what is happening to the neutrinos? Why is this ratio so much smaller than 1? Now, there are two possibilities. One possibility is that the neutrinos are in fact decaying. When they are coming from the sun, they travel a distance from the sun to the earth, and during that time it is decaying. How they are decaying is not known, but they must be decaying, so we see a smaller number. The second alternative is that they are not actually decaying, but these experiments, they are all geared to look for neutrinos of the electron type. Now, if neutrinos have changed their type, they have oscillated, to, let us say, a muon neutrino or a tau neutrino, then these experiments would not see them. They would fail to see the other types of neutrinos. So perhaps neutrinos have oscillated, and that is why we see a lesser number, because we are only counting electron neutrinos and not neutrinos of the other type. Now this problem can be solved. This issue can be solved. Is the neutrino decaying or is it oscillating? And that solution came from this gentleman, Arthur MacDonald, who got the Nobel Prize in 2015 for his experiment. But he said that, look, there is the Z boson mediated process, which is the same for all neutrinos. So if the neutrinos have oscillated to some other kind, to muon or tau type, and I have a detector which measures neutrino interactions to the Z boson, then I will see no depletion. But if neutrinos have decayed, then I will see a depletion. So why don't we try an experiment with only neutral currents with Z boson interactions? So this is what Mr. MacDonald and his collaborators did, the slow neutral current experiment. And lo and behold, he found that the observed number over the predicted number was exactly equal to 1. So neutrinos were not decaying. No neutrinos are lost, only they are changing their type from electrons to some other type, maybe muons or tau neutrinos. How does this mechanism of oscillations work? Well, I cannot go into the detail. It's basic quantum mechanics, but I leave that as an exercise if you like. It's very easy. But what is the mechanism? The mechanism is this, that it's a quantum mechanical phenomenon like the oscillation of a pendulum. In the oscillation of a pendulum, the pendulum changes alternatively from one end to the other, from the left end to the other. In oscillation, a traveling neutrino changes, for example, from an electron neutrino to a muon neutrino, and then back again to an electron neutrino, and so forth. So this is a diagram where I show this, that to start with, I have the electron neutrino with probability 1, and the muon neutrino with probability 0. The muon neutrino is this blue line, and the electron neutrino is the red line. And then gradually the muon neutrino fraction grows. This electron neutrino fraction decreases until this becomes 1 and this becomes 0. And then this goes on back and forth as we travel in time or as we move in distance. Here I have, this is the formula for this probability of a neutrino oscillation of the electron neutrino going to the muon neutrino. And it depends on a mixing angle theta. For this diagram, I've taken the mixing angle to be maximal, to be pi by 4. And then also the oscillation is here as it travels, and this L is the distance which changes. Then lambda is the characteristic length, the oscillation length. So when L becomes equal to lambda, then this sign becomes equal to 1 again. And at pi by 2, when L is lambda by 2, then this becomes 0. So that then you hit the minimum. The oscillation wavelength and hence the probability depends on the neutrino energy and the mass splitting. The wavelength, the oscillation length is given by this formula, where E is the energy of the neutrino and delta is the mass squared splitting of the two neutrinos. So M2 is one of the neutrinos mass and M1 is the other neutrino's mass. Now notice that if neutrinos had been massless, both of the neutrinos had been massless, then delta would have been 0. And if delta is 0, then lambda is infinity, and then you would never see any oscillations. So conversely, the fact that you have seen an oscillation indicates that the neutrinos do have a mass. And so therefore, something is required beyond the standard model of particle physics. It's not a complete story. Now I turn to another property of the neutrino, which is possible, but as yet not known whether it is true. And this property is called the Majorana nature. What is the Majorana nature? Can a neutrino be its own antiparticle? Now, if I ask this question for the electron, people would tell me that I'm crazy because the electron has a charge and the positron, its antiparticle, has the opposite electric charge. But the neutrino is uncharged, so it's possible that its antiparticle is also uncharged as the same particle. And in fact, we do know one particle which is its own antiparticle, and that is the photon. We have never heard of an antiphoton because the antiphoton is the photon itself. And it's not just the photon. The pion, the pi0 meson, is also self-conjugate. It is its own antiparticle. So such things are known for bosons, but there is no fermion which is its own antiparticle. And the question is, could it be that the neutrino is its own antiparticle? In such an event, of course, lepton number would not be conserved because the neutrino has lepton number 1 and the antineutrino would have lepton number -1. So then the lepton number would not be conserved. But how do we know whether the neutrino is a Majorana fermion or not? If it is a Majorana fermion, then the process which is called a normal double beta decay. A double beta decay is like a beta decay, but it's a beta decay twice. So the X nucleus goes to the Y nucleus and 2 electrons are emitted and 2 neutrinos are produced. In fact, 2 antineutrinos would have been emitted. So 2 antineutrinos are produced. But if the neutrinos and the antineutrinos are the same particles, then they could kill each other. So I could imagine a situation where 2 neutrinos are emitted, or another situation if the neutrino is its own antiparticle, when no neutrino is emitted. Now, how do we know whether there is this process or not, whether this no neutrino process is there or not? For that, we have to go back to the original idea of Pauli. Pauli suggested that the neutrino is there because the energy of the electron did not have a unique value. On the other hand, if this process is allowed, neutrino-less double beta decay is allowed, then Pauli comes back and says that now the sum of the total energies of the 2 electrons must be just the same, must be a unique value. So what you do for this experiment is look at neutrino double beta, look at double beta decay and look for a peak in the 2 electron total energy. However, at this point, no such peak has been found. And this can be traced to the fact that if the neutrino is a Majorana particle, its mass is very, very small. This process is allowed provided the neutrino is a Majorana fermion and it is proportional to the mass of the neutrino. Now, if we don't see this process, it means that its mass must be very small. So at the moment, we can only set a lower limit on the mass, an upper limit on the mass of this Majorana mass of the neutrino. How am I doing with time, Professor Ghatak? I have 2 slides on the dark matter and dark energy. Shall I go for that or stop? Professor Ghatak, you are muted. Dr. Jain, somebody please tell me.
Please go
Yes,
ahead.
sir, please go ahead. No issues.
Okay. So then 2 other slides now on dark matter and dark energy. So what is dark matter? You must have all have heard about dark matter. It's a very simple thing, really. There are many evidences for dark matter, but I talk only about the galactic rotation curves. There are stars in the galaxy And one can calculate, one can measure the rotation speed of the stars in the galaxy around the center. And one finds a distribution like this, a green line. This is the distribution of the rotation velocity which one finds. However, so here, this is the galaxy size. So the galaxy basically ends here. Now, what you expect is, if you follow the Kepler's laws, then what you expect is once the stars go beyond the size of the galaxy, their rotation speed will fall. Obviously, if the star is far away from the galaxy, it will have no rotation speed around the galactic center. So it should fall like this. However, what is seen is that it remains fairly flat. So what's going on? So the dynamics is not giving this result. Now there are people who say that so Newtonian dynamics has to be modified, but that's a minority point of view. The usual view is that there are in fact particles. The galaxy size that we note here is the visible size. But in fact, there is more matter in the galaxy, which we call dark matter, which goes far beyond the visible size. So the size of the galaxy, in fact, is much larger, and there's dark matter in the galaxy. Particle physics has several candidates for dark matter. Now, since we don't see this dark matter, obviously they must be essentially non-interacting. They must be almost non-interacting, and also they must be stable because they are sitting there without decaying. If they had decayed away during the evolution of the universe, then there would be no dark matter left. So there are candidates of such dark matter, like the lightest particle of supersymmetry, or in some models of particle physics, where there are more dimensions than 3 + 1, which are called Kaluza-Klein particles. The lightest Kaluza-Klein particle is an example. So there are these other kinds of particles which could be stable and almost non-interacting, and which could play the role of dark matter. At this moment, we have not succeeded in detecting any dark matter particles on Earth. Experiments are around, but so far there has been no clear evidence. Finally, I want to talk briefly, very briefly, about dark energy. What is dark energy? Now, of course, mass and energy are equivalent, as Einstein has told us. So I have no apology to make to talk about dark energy in this talk. Now, dark matter is mostly clumped around galaxies or clusters of galaxies and so on. But evidence points towards some energy distributed uniformly in all space, and in fact that is the dominant part. The dominant part of the energy, about 75%, is dark energy, and the 23% is dark matter, and the rest, this is what we see, the stars and galaxies and so on, the neutrons and protons and electrons and so forth. The evidence for dark energy comes from distant supernovae, from the anisotropy, the cosmic microwave background, and in structure formation and so on. And the particle physics interpretation of dark energy is not clear at the moment. But what is the evidence? How do we know that there is dark energy in the universe? Well, those are the evidences, but there's one qualitative way in which we can understand that there is dark energy. And the qualitative way is the following. The expansion rate of the universe should be slowing down due to gravitational attraction of matter. Now, I'll give you an analogy. If you throw a ball from ground upwards, then what do you expect? You expect that the speed of the ball will slowly will reduce slowly. Finally, it will come to a stop, and then it will start falling down. The universe is expanding from the Big Bang, and we expect the universe to gradually slow down, perhaps come to a maximum, and then reverse due to the gravitational attraction, due to reverse and come back. So that is the motion that we expect. But what we find is that the universe, which should be slowing down due to the gravitational attraction, the observations indicate the acceleration was actually less earlier, not more. In fact, the acceleration has increased, which means that there is not only some matter, but this is a repulsive matter which has increased the acceleration. So this is dark energy, and we still do not have a satisfactory candidate for dark energy. So these are all open issues which the future holds for us. So what do we have looking ahead? There are many, I have discussed with you, many manifestations of mass. I'm afraid it has been very qualitative. I could not go into any technical detail because I wanted to address a very wide audience. So I just mentioned some of the open issues which I didn't touch upon. For example, though gravity, we know the existence of gravity, we do not have a satisfactory unification of gravity with the other interactions. For that, like the other interactions, we need a quantum theory of gravity. And we do not have a quantum theory of gravity at the moment. Also, there is speculation that perhaps the general theory of relativity, which has certain issues which people sometimes question, for example, that gravitation would always lead to singularities, and people think that perhaps there will be alternate theories of gravity which will avoid problems like that. Also, quantum theory of gravity is an open issue. So there's a lot of work going on here, including in string theory, which ties up particle physics with gravity. Then there must be physics beyond the standard model, because neutrinos have a mass. There is dark matter which cannot be explained by the standard model. So the standard model is very good, but it's not the total story. So you have to go beyond it and then test these other newer versions which are coming out. So all those things have to be done, and those are in the future. Then we still do not have a good understanding of the origin and type of neutrino mass, whether it's a Majorana particle or not, how does the mass originate, what are the mass relations, and so forth. So work is going on here. And naturally, physics is an empirical science. So you cannot do anything without experiments. And many experiments are going on worldwide to address some of these issues, including at the Large Hadron Collider at CERN, about which all of you have heard, at the B factories, one of the B factories running now, the asymmetric B factory in Japan. And then the neutrino experiments, for example, this one at Fermilab, and many others in, for example, China, Korea, Europe, and elsewhere. In India, there has been a very long time plan for the India-based Neutrino Observatory, which is an extremely interesting experiment which could lead to many important results. But unfortunately, not everybody sees eye to eye with science, and that leads to a lot of problems. And the India-based Neutrino Observatory is stalled because of judicial reasons and so on. And of course, the last point which I touched upon, the dark matter, this is still an open issue. It has been a pleasure. I thank Dr. Srivastava once more for asking me to give this talk, and I thank Professor Ghataksar for his kind introduction, and for all of you for your very good patience. Thank you very much. Thank you.
Thank you so much, sir. for enlightening our audience with such a knowledgeable lecture. Now there are so many queries in the chat box, so the session is open for questions, and I would like to request Dr. Yogesh Kumar to conduct the question session. Over to you, Yogesh sir.
Thank you so much, ma'am. Before taking questions from the participants, I would like to extend my hearty thanks to our distinguished speaker, Professor Ray Chaudhary, for enlightening us with such an informative lecture on the mass of small things. Sir, you have explained the topic in a very lucid and insightful way. I hope our audience are happy to have you here today. Thank you, sir.
Thank you, Dr. Kumar. Thank you. You are very kind. Thank you.
Yeah. Sir, I can see a lot of queries from the participants, so I can take some of questions for you.
Yes,
So first question here is from Mr. Rohit Tomar. Can we take mass as fifth fundamental force of for universe? And if yes, how it can change the understanding about worlds around us?
It's possible that there is a fifth force, but mass is not a force. Mass is something else. Mass is it's basically a constant which enters, as I said, in the gravitational force, in the inertial Newton's law, or if you like, in the great formula of Einstein that E square minus B square C square equals M square C4. But the question is important because a lot of people believe that there might be a fifth force, and experiments are going on to look for a fifth force. In that case, there will be small deviations from the gravitational interaction between two massive particles, and these experiments are going on.
Okay. So next question is that in terms of interaction as said by Feynman, can you please explain why increasing speed make a particle more massive while traveling in vacuum as predicted by special relativity? And second, in continuation of that, what kind of interaction is associated with increase of speed in vacuum? And this question asked by Mr. Ankat Man.
I'm not sure I understood the full question, but let me try to address the point. What Feynman had said, and this is a general consensus, that if there are interactions, then they tend to hold things back. You can just imagine yourself, if two of your friends are holding you, you will find it difficult to move. That's an example of an additional inertia. So it is just this inertia which is due to the interactions which Feynman had pointed out. Now, the speed of light in vacuum is, as you said, is the maximum, and that continues to be so in spite of the Higgs structure of the vacuum, which I spoke about, because light is due to photons, and photons do not interact with the Higgs field. So as far as light is concerned, the Higgs field in the vacuum is as good as absent. So therefore, light continues with its speed as before. It is not affected by the Higgs field in the vacuum.
Okay. So next question is from Soumya Shri. Higgs boson has mass. If its mass less, how it gives mass to other particles?
It's a very good question. I'm happy that this question has been asked, and I'm afraid I have not discussed this. I have not, you have said that the Higgs boson is massless. I have not said that. I have never mentioned that. I had avoided this question. But since you asked, I have to tell you that I have to go back to what I said in my talk, that all masses arise from interactions with the Higgs field in the vacuum. So when the electron or the W boson, they pass through the vacuum, they interact with the Higgs field and they get a mass. Now, what I did not talk about, and that is that the Higgs boson interacts with itself. Now, this is complicated business. The Higgs boson interacts with itself. So therefore, when the Higgs boson passes through the vacuum, it interacts with the Higgs boson and it develops a mass. So the Higgs boson is not massless. It is in fact massive, and its mass is determined by the strength of the self-coupling. The self-coupling is the coupling of the Higgs field with itself. And there's a standard formula using which one can calculate this Higgs boson. Now, the Higgs boson mass. Now, there are two constants in this self-coupling. So, in fact, you can only determine a formula. But now, through experiments, we have measured the mass of the Higgs boson. So, those constants can be determined. It's a good question. I didn't answer that. I didn't cover that in my talk.
Okay, thank you, sir. Next question is from Adarsh Gupta. What is small m? I think he's talking about neutrino mass. And why is it 0 when there is only left-handed and right-handed component?
Okay, yeah, I'll try to give that argument. I'll do the converse. Imagine that a particle has a mass. It's not mass 0, but rather it has a non-zero mass. Now, if it has a non-zero mass, then the argument which I gave is that it can move with a high speed, if you like, but it cannot move with the speed of light. So you can always imagine that there's another frame which is moving faster than this moving particle. And in that faster moving frame, this particle would appear to be going backwards. So its momentum would be reversed, its spin would be unchanged. So what was left-handed would become right-handed and vice versa. Now this argument says, therefore, that if a particle is massive, then whether it is left-handed or right-handed will depend on the reference frame. So therefore, it has to have both these components if it is massive. Then it could be left-handed in one frame and right-handed in another frame. But if it is massless, then it is always moving with the speed of light. And then you can never go to a frame in which you can reverse its direction of momentum. So it can always remain either left-handed or right-handed, but it doesn't need to have both components. So therefore, the argument which I gave was, if the particle has only left-handed component or only right-handed component, then it is massless, but it has to have both components in order to be massive. This was the argument which I had given.
Okay.
I think that should answer your question.
Yes, sir, I think so. Next question is from Wasim Basir. The knowledge of elementary particles and their interaction has led to some important discoveries, but the principle of emergence seems over the year is key in understanding how different principles can just emerge from some symmetries and relevant fixed point. For this, please give your comments, sir.
I'm not sure I understood the last part. What was the last part?
So the last part is that the principle of emergence seems over the year is the key in understanding how different principles can just emerge from some symmetries and relevant fixed points.
Well, I don't know exactly what is meant, but how does an interaction emerge from a symmetry? Let me think. It's not easy to come up with an argument for this, but I'll try my level best. Look at it this way: in quantum mechanics, we know that everything is really represented by quantum mechanics, and in quantum mechanics, we have what is called a wave function. So, for example, the electron has a wave function, And the wave function is a complex number. In fact, if I say it's a complex number, I've not done a good job. It's a complex field, that is, it's a complex function which varies from point to point. Now, when you have a complex function like that, then you can change its phase from point to point, and this is a symmetry. This is called a gauge symmetry. It can be shown, and this I cannot show you now, that this change in this complex phase of the wave function is tied to electromagnetism. That's the simplest case. For more complicated interactions, there are more complicated phase-like transformations, which I call gauge transformations. And those gauge transformations give rise to other interactions. So it's basically, it relies on the complex nature of the wave function in quantum mechanics, and then symmetries associated with the wave functions, and those symmetries give rise to interactions. It's a complicated business.
Okay. Ankanman is asking that what are the future possible alternatives of the standard model?
You see, there are many alternatives because there are a lot of particle physicists in the business. So they have to keep themselves busy. So they imagine various ways in which the standard model can be expanded. They introduce more particles, more symmetries. For example, supersymmetry says every fermion has a boson associated with it. And there are also theories in which new dimensions, space-time dimensions, are introduced. So various ways of extending the standard model are being studied. But the more important thing is to experimentally verify them. What we dearly need now is new experimental results which contradict the standard model. The standard model cannot explain those new results. Only when we see such new results, we will have some signposts on the basis of which we can focus on the correct extension of the standard model. At this moment, too many extensions are being worked upon.
Okay, thank you, sir. Next question is from Dr. Partha Goswami. Interaction breaks symmetry, which users in phase change?
Which involves phase change?
Yes, sir.
You know, these questions are very important and interesting, but they cannot be explained so easily. I'm sorry, I'm afraid, this would require several slides for an explanation, and I've not prepared any such slides for this talk.
Sir, you are on mute.
Okay,
Yeah.
so let me repeat again. A phase transformation, how does a phase transformation affect, how do we see the effect of a phase transformation? If the phase transformation on a wave function depends on position, then remember that momentum is basically a derivative in quantum mechanics. And then the derivative will also act on that phase. If the phase depends on position, then the derivative will act on the phase. So therefore, the momentum will change because of that phase transformation. And to compensate for that change in the momentum, one has to add what is called a vector potential. The vector potential, as you know, is what is at the origin of the magnetic field. So that's how the electromagnetic field enters through a phase transformation. So these are all related, but it's too difficult to explain in a minute or two. You should look up a book. This is widely discussed. It's a standard discussion.
Okay, thank you, sir. Next question is that the Higgs field is neutral, so that photons do not interact with it. What is meant by this neutrality, and how would non-neutrality lead to the interaction with photons?
Okay, here what I meant was the following, that the photon couples only to charged particles. The photon does not couple to uncharged particles. Now the Higgs field is, the Higgs boson is an uncharged particle. It has no electric charge. So the photon will not couple to it. The photon will couple to charged particles like the electron or the proton, but it will not couple to neutrinos, which are not charged. Now, because the vacuum, according to Peter Higgs, is full of the Higgs field, anything which interacts with the Higgs, boson would develop a mass while it struggles to go through the vacuum. But the photon, as I said, does not interact with the Higgs boson, and therefore it merely goes through the vacuum and it does not develop a mass. So it all boils down to basic electric charge. We're talking here about electric charge. The Higgs field does not have, the Higgs boson does not have an electric charge. Dr. Kumar,
Okay, yes,
how
sir.
many questions do we have?
So there are a lot of questions, but 5 minutes.
Yeah, maybe you
yeah.
can use your judgment and
Yes. Sir, we can take last 2-3 questions more.
Okay.
Yeah.
2 is okay.
Yeah. So next question is that how do we know the estimate of dark energy and matter in the universe?
Oh, this is done through astronomical measurements. There are various astronomical measurements which go on. For example, from supernovae, supernovae are these explosions which have taken place much before, and the light now reaches us. And so from the supernovae explosions, we receive the light, and from the way they are redshifted, we can tell what the acceleration was when the explosion took place. So from that way, we can tell how the acceleration of the universe or the deceleration, how it changed over time. It also can be seen through the anisotropy of the cosmic microwave background radiation. The cosmic microwave background radiation, as you know, arises from the Big Bang and is a remnant of the Big Bang. And it's a very 2.7 degree Kelvin radiation, which is everywhere in the universe. Now, normally we say that it is uniform, but there are very small fluctuations. And as we have progressed in our understanding, we have gone beyond the uniformity. Now the study is on the non-uniformity, very small scale, but still the non-uniformity of the cosmic microwave background radiation. And from those studies too, one can find out about dark energy and dark matter. And similarly, there are other observations which tie up with these results. So there's a complex way through which one arrives at that formula where there's a distribution of dark matter, dark energy, and the observed matter.
Okay, thank you, sir. Now I can take the last question of this session, which is asked by Dr. Partha Goswami. And yes, the participant, if has more question or query, they can directly ask with the permission of Ray Chaudhary, sir.
Yes, they can send me an email, and I will try my best to answer.
Yes, thank you, sir.
But I may take some time.
Yes.
I'm not one of those persons, as Dr. Jain knows and Dr. Srivastav knows. I do not answer very easily to my emails.
Yes.
It will take time, but I will answer. I can.
Sure, sir. Sure, sir. So the last question is that while most fundamental particles obtain their masses from interaction with what's called the Higgs field, as revealed by the discovery of Higgs boson. The neutrino may get their masses in different manner. What is your comment? And in continuation of this, there is a second question. How do you distinguish between the neutrino and antineutrino? Is it magnetic moment?
These are also interesting questions. How do I distinguish between the neutrino and the antineutrino? Let me take up that question first. Neutrinos are coming from the sun and from the atmosphere and so on and so forth. Now let us take the neutrinos coming from the atmosphere. Now in the atmosphere, both neutrinos and antineutrinos are produced. Now supposing a neutrino interacts with matter, it's very rare, but supposing a neutrino does interact with matter, then if it's a muon type neutrino, then it would produce a mu minus particle on the interaction. Had it been an anti-neutrino, then it would produce the antiparticle, that is the mu plus. So a neutrino would produce a mu minus, an anti-neutrino would produce a mu plus. How would we distinguish the mu minus from the mu plus? We will apply a magnetic field, and then the charged particle will bend differently in the magnetic field. So from the bending direction of the charged particle, we can tell whether it's a mu minus or the mu plus, and then trace back that the interaction was due to a neutrino or due to an anti-neutrino. This was the key idea which was thought of in 2002 for the India-based neutrino observatory. And had it been started at that time, it would have shaken the world by today. But India is an unfortunate country, and we have still not taken off. So it's a very good question. It's an important thing to distinguish between neutrinos and antineutrinos. There is no detector so far with a strong magnetic field, which the India-based neutrino observatory was planning, that would distinguish between the neutrinos and antineutrinos, and that would make key observations on neutrino properties. And unfortunately, that has not taken off. And now other experiments are planning in different ways to distinguish the same thing that you asked, neutrinos and antineutrinos. The question about neutrino mass, how can the neutrino mass originate? That is a difficult question. One thing is that the standard model doesn't have a right-handed neutrino. So you could just add a right-handed neutrino by extending the model and say that it has a similar Higgs-like mechanism for generating the mass. But that would be ugly because the neutrino mass is so very small that such small masses would not tie well with the other masses of quarks and leptons. So various models are being postulated for the seesaw mechanism and so on. Please look up the internet with the seesaw mechanism for neutrino masses, and it will tell you other ways of getting a light neutrino mass. It's an active subject.
Yes. Okay, sir, I still can see a lot of queries from the participants and many very good comments. But I am very sorry that I cannot take more questions due to the shortage of time. So thank you so much, sir, for handling the queries of the participants so graciously and sharing your wide knowledge of spectrum. Now, I would like to invite Dr. Poonam Jain for proposing vote of thanks. Poonam ma'am, over to you.
Thank you, Dr. Kumar.
Thank you, sir.
Thank you so much, sir. Once a great man whispered, feeling thankful and not expressing it is exactly like wrapping a present and not giving it. Today, I take the opportunity to put all my gratitude into the words. On behalf of the entire Indian Association of Physics Teachers Regional Council 1, I wish to extend my hearty thanks to our eminent speaker, Professor Amitabh Ray Chaudhary, sir, for taking out his precious time and accepting our invitation to deliver such a wonderful talk. And it has been quite informative for all of us. Thank you so much, sir. I extend my special thanks to Professor Ajoy Ghatak, sir, for sharing his timely support and being with us today. We are thankful to him for the necessary support in this webinar. Also, it is a pleasant coincidence that two distinguished physicists of the country are today together with us. One of them is Professor Ghatak, the President of National Academy of Sciences, the oldest science academy in India, whose founder president was Professor M.N. Saha sir. And Professor Amitabh Ray Chaudhary held the chair of Palit Professor, which was once occupied by Professor Saha sir. This coincidence, we and the participants are going to remember for years to come. Thank you, Ghataksar. I wish to extend my gratitude to Dr. Om Prakash Sharma, the member of National Executive Council of Indian Association of Physics Teachers, for the continuous guidance, inspiration, and support. I would also like to acknowledge my gratitude for Professor V.P. Srivastava, sir, the President, Shri R.K. Tiwari, sir, the Vice President, Dr. M.S. Bhandari, sir, the Secretary, and all the other Executive Council members of Indian Association of Physics Teachers for their motivation, guidance, and encouraging the webinar activities of IAPT. Sir, all of you have always been a source of inspiration for us. Many thanks to all of you. Without the constant support of all of you, this webinar series has not seen the light of the day. The entire team is also grateful to all the members of Indian Association of Physics Teachers, Regional Council 1 and Delhi State Science Teachers Forum who have joined us today and for their support and encouragement. They are always ready with their thoughts and support. Needless to say, I would also like to extend a big thank you to all the participants, including the teachers and the students from various national and international universities like Delhi University, IIT, IISER, NISER, and many more for their active participation and sharing their time and patiently listening to the proceedings of the series. Last but not the least, before we close the event, this vote of thanks is incomplete without acknowledging our team webinar. I have been fortunate enough to be supported and hence given a chance to work with a team of very motivated and dedicated colleagues, Dr. S.K. Singhal and Dr. Yogesh Kumar. I extend my sincere thanks to both of them for their enormous cooperation in the organization of this event. Before proceeding further, there are few announcements to the participants that today we have no attendance link and that the same will not be shared in the chat box. Those who have attended the webinar via Zoom will be entitled for the certificate. Also, those who have missed lecture conducted in the first series in 2020, also the lecture conducted in this month of July 2021, can view them on our YouTube channel, that is IAPT RC1. The discrepancy between what was expected and what has been observed has grown over the years, and we are straining harder and harder to fill the gap. With this, we have come to the end of this wonderful event. Before we let you leave, I request everyone to kindly turn on their cameras for a few snapshots so that we can relish the moment of the day. We appreciate everyone's presence virtually in this event. All the participants who attended via Zoom will be provided with the e-certificates within a few days. Your patience will be appreciable. Thank you everyone for joining us today. Have a great day ahead.
Thank you very much, madam.
Thank you, sir. Thank you.
Thank you, sir.
Thank you so much, everyone.
Sir, I can see a lot of appreciation in the chat box regarding your lecture. People have enjoyed every bit of this lecture.
Yes. And special thanks to all the participants who attended our online series.
Thank you all the eminent professor present here, all the participants. Now I am ending the meeting for all.